And the first talk is going to be on Hydra, Generalizing Peephole Optimizations with Program Synthesis. And the talk will be given by Manasij Mukherjee.
Hi, everyone. Is my mic fine? Okay, awesome. I'm going to present our Hydra, which automatically generalizes peephole optimizations. This was the major part of my PhD thesis. I graduated a few months ago. And this is joint work with John over there. I'm going to start with the motivation of why we want to do this, and then I'll get into the meat of the talk, how it happens, and then briefly present the results. Now, about the motivations, let me start with what peephole optimizations are. They are pattern-based local rewrites that do not change control flow. The name comes from an era of compilers where optimizations used to happen on a small sliding window of instructions. That's no longer the case. We match patterns and replace them with simpler patterns. Here is a very simple example of a peephole optimization, which is an application of De Morgan's law. Now, what does it mean to generalize peephole optimization? Optimizations. Here is a slightly more involved example where we can replace a slightly larger bit of code, a pattern, with a really small expression. This is not really general. The first hint comes from the fact that you have the x is a 32-bit vector, and you have a bunch of constants. The way to make this general is to remove the restriction that x is 32 bits and turn the constants into symbolic constants. So here is a more general version of this. There is a little bit missing here, which is this only works when c is a power of 2. And this is the fully general version of the thing in front, thing on top. And this is what we mean by generalizing a peephole optimization. Let me take this opportunity to introduce the notation we use. The precondition is on the left, and we have this models sign, meaning that precondition is assumed. And then we replace the LHS with the RHS. So why would we need to automatically do this? Like, can a human not do this? Well, humans have been doing this. Like LLVM's peephole optimizer is called instcombine. It is written in 40,000 lines of really dense C++ code. More than 400 compiler developers have worked on it for about 20 years. And this instcombine is still full of bugs. New bugs are found every day. C. Smith has found a huge number of bugs in instcombine. And even if LLVM and GCC exists, can you really do this for the next compiler or the next 10 compilers? So we need some way to automatically construct peephole optimizers. But we realized all these things after most of the problem. So why did we start to solve this problem? It comes from super optimizers. So we worked on a super optimizer called Super for LLVM IR for a really long time. And we realized that the rewrites found by Super were really specific to the code we want the super optimizer to optimize. But a compiler like LLVM's instcombine, a peephole optimizer, requires really general transforms. So something Super finds would take a significant amount of manual effort to contribute to LLVM. So this is where this Hydra tools comes into play. It automates this hard part. It turns out that finding these rewrites is actually the easier part of the problem, and making it more general and suitable for LLVM is the difficult part. So in some sense, Hydra is a bridge between Super and LLVM. And the theory we have developed enables super optimizers to be useful in practice. Let's now get into how to actually do this. Hopefully that was enough of a motivation. Let's start with a very simple example, which is 32-bit x multiplied by 8 can be simplified to x left shifted by 3 bit positions. The most general form of this is when c is a power of 2, you can replace that with the left shift of the log of that constant, of that symbolic constant. There are 3 steps to this synthesis problem. First is you have to synthesize a constant expression for the right-hand side. Here that's log of the binary log of the c. Then you have to find a precondition that makes the optimization work. Otherwise, it's incorrect optimizations, which can pose a fairly tricky amount of debugging in a compiler. And then you have to make sure it works for all widths, or at least the widths you care about. I'll talk more about the width independence part of this later in this talk. For now, let's focus on the synthesis aspect of this. The first part of the first aspect of synthesis here is converting the constant to symbolic constants. Here we have 4 and 2, and we convert that into C1 and C2. And once you have these symbolic constants, Hydra uses 2 different synthesis techniques to find the expression which is C1 minus C2 here. The first is inductive synthesis, that is synthesis from input-output examples. Here, the 4 and 2 in the left-hand side are the input examples, and the 2 on the right-hand side is the output examples. This works really well for arithmetic operations like addition and subtraction. For bitwise operations like AND, OR, and XOR, or even other random operations, enumeration tends to work a little bit better. So we augment enumeration with sketching and components to find these constant expressions. The second part is finding preconditions, which makes the optimization valid. An important part about these preconditions, a compiler has to be able to prove these preconditions right for a particular LHS. For that, we normalize all preconditions to data flow facts. After that, Hydra enumerates and filters these synthesized preconditions to find something valid. This part has been many times before. AliveInfer is a really good tool that does this better than Hydra, in fact. Our only tricks are normalizing it and then quickly ranking them using model counting. You might be wondering, like, how we deal with these 3 nested synthesis problems, and model counting is known to be a fairly heavy thing on top of this. The secret to that is reducing the width of the expressions, the optimizations. So here, you see here a simple optimization of a 64-bit integer, and there is an unsigned division in the left-hand side. It's fairly difficult for a SMT solver to deal with this kind of expressions. So we reduce the width to a really small width, like 2, 4, or 8, whatever is applicable. And then we run Hydra on this. This makes it 20 times faster. And now, when it's 2 or 4 bits, you can brute force the model counting aspect of ranking the preconditions. Because there are like 4, 8, or 16 possibilities. You might as well count all of them. And after it's a really small width, you can verify the type assignments, or all possible type assignments up to a threshold, because the SMT solver queries are really, really fast when it's a small width, as opposed to 64 bits. To recap, we have 3 synthesis loops. The first one is finding constant expressions, then finding weak precondition, and then verifying the type assignment, its width independent, up to some threshold, because you cannot verify an arbitrary number of widths. We hope there are tools in the pipeline, the research pipeline, that makes it possible to solve this problem in general. But for now, we enumerate all type assignments. Let's get into the width independence aspect of this, because as you have seen, we cannot directly verify width independence. So what we can do is make sure we synthesize expressions and preconditions that are width independent inherently. And the main issue with that is constants. For example, this optimization, like it's the same example, x multiplied by 8 to x shifted by 3, works for widths more than 4. If you truncate the values, it no longer works. But the general form of this, which doesn't have concrete constants, it is independent of bit width. So the solution is clearly to get rid of all the constants. And so far, with what you have seen, finding constant expressions and good preconditions, we do this without synthesizing new concrete constants. But there can be constants which are not easily convertible to symbolic constants. For example, here you have x 32-bit variable shifted left by 32 bits. It produces Poisson. Poisson is a form of undefined behavior in LLVM. So shifting past bit width is Poisson. But this is obviously not general enough, because this optimization has to work for multiple widths and multiple constants. The first step towards generalizing is introducing a symbolic width constant. So now x shifted by the width of x is Poisson, but this is not general enough. We can synthesize a precondition which says that if you shift x by c, which is greater than the symbolic width, You produce poison. You can replace that expression with poison. This is the most general form of this. We are going to see this pattern multiple times in the next few slides, so be sure to familiarize yourself with this. What are the other possibilities for finding these constants in optimizations? And this usually comes from super optimizer derived optimizations. Here is a simple example. It says that if x falls within 2 and 10, 10 is not included in the range, then x less than 10 is always true. So if you can prove that fact, you can replace x less than 10 with 1 or true. LLVM or other compilers do this by doing a range analysis. Here CR means constant range. And if you're implementing the optimization, you would write something like this, which is if you statically analyze x, and if all these conditions are met, you replace this expression with 1. Here 1 means true again. So symbolically, this means you write that if x is less than the upper bound of x, that expression is 1. The interesting thing to notice here is that we are exposing implementation details of static analysis or abstract interpretation to the declarative form of the Peephole optimization. And we realized that this thing, the compiler developers have been doing this for a long time, but this had not been formalized yet. Like, are there specific things you can do with this, or are there specific preconditions that are not allowed? So this had not been formalized. And again, the general form of this is you take that x less than upper bound of x, synthesize a new precondition to make it slightly more general. And this is indeed what LLVM implements for in the inst simplify pass. Let's talk about a slightly more involved example of this using the known bits abstract domain. This one these three optimizations here show that if you can prove some specific bits of a variable are 1, provably, you can replace x or some constant with x. And there can be an exponential number of these patterns. You can replace this exponential number of patterns to match with just one single pattern, and this is the most general version of this. And we are calling these symbolic names data flow variables. I don't know if there is a better name for this in literature. If there is, we apologize for inventing a new name. Here are some more examples utilizing data flow variables. You have seen these two before. We created another data flow variable called demanded. Demanded means it corresponds with the demanded bits abstract domain of LLVM. And it's basically a don't care analysis. And this is the optimization we could create that uses these data flow variables. It means if a bit of a variable is known to be 1 or 0, or if it's demanded, you can replace it with a constant. Moving on to the results, the high-level result is that once we generalize optimizations with Hydra, they match much more often. The red part of this plot is the amount of matches the Hydra-derived optimizations have, versus the blue part is from super, that is the ungeneralized optimizations we have from a super optimizer. But this doesn't really help us if the tool cannot help compiler developers. We went through the LLVM's issue tracker on GitHub and crawled through these optimizations, ungeneralized optimizations that the developers had posted on the issue tracker. Hydra could generalize about a little bit more than 3/4 of those optimizations. Here are two examples of that. It's a little bit tricky to understand from the slide, but the second one here is the example I had in my second slide. And once a developer uses Hydra to create the general form of an optimization, Hydra has an implementation to automatically generate the C++ code that you can drop into LLVM's inst combine for it to work seamlessly. This looks simple enough, but this gave me quite a bit of headache to implement. Now moving on to the analytical part of this, even with a fairly crude comparison, the optimizations found by super and generalized by Hydra can come close to, to be comparable to inst combine, which has a lot of developers working on it. I'll draw your attention to the light red part of this line, which is LLVM automatically inlining an abstract value function to giving it an unfair advantage. We implemented that as a special hack to basically make to comparison there. The generalized optimizations match more often, and we can create an optimizer competitive with LLVM like this. And Hydra can generalize real-world rewrites. Tracker. My talk on Hydra.
Questions?
Hi, really nice talk. I have a question about the preconditions. So you said that they're weak, but is it the weakest, or do you care about the weakest?
Okay, good question. Let me try to, so if we have preconditions which are just data flow variables, we can find the weakest by climbing the lattice. If we have to have expressions with symbolic constants, there is no way we can find the weakest one. We can find the weakest one we have discovered by our enumeration. So out of the ones we have enumerated, we can find the weakest one.
Yeah, so great talk. I was trying to understand better within Hydra how much work you have to do for each data flow analysis. So if a new data flow analysis is implemented inside the compiler, what work do you need to do inside Hydra in order to be able to learn preconditions involving its variables as part of your system?
It's fairly pluggable right now, but there might be hidden assumptions about new data flow analysis that we might not have already thought of. For example, in my sorry about the constant flipping here. So the last thing here, which is really general, but it turns out that this doesn't really work for LLVM because LLVM does not guarantee that the ones and zeros you find for a variable that is not demanded are accurate. So it guarantees only accurate results only if the variable is demanded. So if you have hidden assumptions like this, you might have to hack the system quite a bit. But as long as things are more declarative without hidden assumptions, it will work. It's plug and play.
Okay, great. Any other questions? One more question.
Thank you for your talk. In the results section, you mentioned that your approach comes close to inst combine.
Mm-hmm.
So would you then suggest the developers to switch over to your approach and not work on inst combine anymore?
So in the long term, I think something like that has to happen because for new compilers, you can't develop a new inst combine every time. For now, switching to make immediate sense. But we have not worked on optimizing how fast it runs yet. But assuming you don't care about how fast it runs, you can switch over today.
Okay, thank you.